All right. The nature of a scientific law. We are on page 34. And there, if you notice, there is no real blue. There's no definitions. There's only a short couple paragraphs with the integration portion. There's really only one page of content left. So this is maybe poor planning on my part, but this probably could have been rolled into a quick couple-minute presentation in a previous class. And because it's not very technical, we're going to find out the nature of a scientific law. There's a sequence that takes place in the determination of a scientific law. Now, when you hear the term law, what kind of words come to mind? What concepts come to mind about a law? Pardon? The amendments? No. I mean, think about everyday life. A law is a free response. A law is a rule. Okay. A law is a rule. A law is a standard. A law is also in science, a law is a assumed truth. Okay? It's true. Now, it's not perfect when we talk about civil government and things like that. Because, like, for example, in Louisville, are you supposed to drive through red lights?
No.
No! So in Louisville, nobody drives through red lights, right?
Yes.
Yes, they don't. Or no, they don't, which that means they do. It's a double negative. Start working on your language arts. Okay, so, I'm kidding. So here's the deal. When we think of civil government, it's also, people have to obey those laws. It's a rule, it's a standard, people have to obey it. When we talk in science, we're talking about a law. It's something that is presumed to be always true. It's a standard. It's a principle. How does something take on the weight, the authority? How does it take on the authority of a law? Well, everything starts out very simply as an observation. I see something. I notice something happening. And I just look at it and go, there is some principle at play here. There is something happening. Maybe as a little kid you noticed that every time you tripped yourself, you fell. You tripped yourself, you fell. You tripped yourself, you fell. And after a while you said, if I trip myself, I will fall. Because you observed that as you tripped yourself, as you were still working on that fine motor control, and you brought your leg up behind the other one, you would fall. Then you started to hypothesize and say, if I trip myself, I will fall. Some of you said, I'm not so convinced, so I'm going to test it. Oh, fall. Over and over again. You say, you know what? I observed that whenever I trip myself, I fall. I think if I trip myself, I will fall. I tripped myself and I fell. Therefore, I have a theory. When I trip myself, I will fall. Okay? A theory. Maybe the theory is a little more specific and a little more mature than that. Whenever I drop something, it falls. I drop something, it falls. I think that there's some force at play that when I drop things, they will fall. At least I appear to fall. Let me drop some things. Boom, boom, boom. Guess what? Everything I dropped fell. Oh, wait a minute. I just dropped a helium balloon. It didn't fall. I thought everything that I dropped fell. That didn't fall. What's going on here? You come up with a theory of why things fit or why things don't, and you perfect that a little bit more. And how do you perfect that theory even more? You do more testing. And after, another technical term, gobs and gobs and gobs and gobs of testing, guess what? You kind of figure out what's going to happen to the point where you can predict what will happen in every known occurrence. And then you have a law. Now, there is no committee that sits out there and says, this theory is now a law. It's a consensus of people. We say the second law of thermodynamics, for example. talk about entropy. Everything is in a state of decay. Who decided that that was true always? It was consensus. It was the scientific community. And because it's a second law of thermodynamics, that term law means that people assume it to be true, because so far it's been proven to be true every time it's been tested in the way that it's been articulated, the way it's been understood. So here's the point. I see something, I come up with an idea of why it's happening, I test my idea. If my idea tests true repeatedly, it becomes a theory. If I test it and I find nuances and differences in it, I tweak my hypothesis. I get a more and more and more specific hypothesis. And when I test that, if it keeps working out, it becomes my theory. And my theory, replicated over and over again, repeatedly, gets to the point of so much authority that it becomes a law. And people, when it becomes a law, often presume it to be true and just accept it and move on. If I'm doing an experiment that depends upon this remote falling, I don't have to sit here and go through a whole testing process to, first of all, prove that it will fall. You assume, as I do, that the law of gravity will be at play and the clicker will fall. So we assume that because it's a law, and we move on from there. So in physics we say, if I throw this at a certain velocity, at a certain angle, how long will it take it to drop? You don't go, I don't know, will it even drop? No, it'll drop. Why? The law of gravity is at play. If I'm going to question whether or not it'll drop, then I've got to go back and do testing to see if the law of gravity is true or not. Okay? So one of the ways that this sometimes gets messed up, and talking about the amount of authority that we give to laws or give to theories, is sometimes we take a theory and we make it a law. For example, and just because, Christian school context, the theory of evolution as opposed to the law of evolution. Why is evolution a theory and not a law? We can't prove it. We can't test it. We can't replicate it. I mean, even to the degree of seeing slight variations, we can test and see that over time. But yet the quantum jumps necessary, the major movements needed for evolutionary theory to be true, have not been replicated, cannot be produced. We have evidence that we look at from history that can be interpreted to support it, but there are also alternate explanations that cannot be disproven. So at the most, because we can't test it and prove it, it has to remain a theory. It's not a law. Now, many times people take that theory and treat it as if it is a law. And they'll say, well, we know that over a period of millions and millions and millions of years, this happened. Therefore, I'm doing a research paper right now on attachment theory. And classic attachment theory is based upon an evolutionary principle. What that means is it's common for everybody. Everybody should go through the same process because it's rooted in evolutionary theory, not law. But again, the presumption is that evolution is true. Okay? But we can't give it the status of a law and say it is true because we cannot test it. We cannot replicate it in a lab. We cannot show evidence that it's occurring in the way that it's required to occur for it to be a law. So it's the theory. So you need to be smart enough and wise enough or discerning enough, however you want to look at it, to recognize when theories are being treated as laws or when a hypothesis is being treated as a theory. Because frankly, when you're in a field and you're doing that much study, that much research, that much work, there is a tendency to elevate the authority of the stuff you're studying. There is a tendency to make a hypothesis a theory and to make a theory a law. And you need to be careful not to do that. But then again, who's to say it's not a law? Since there is no body of arbitration that says, today, just so everybody knows, as of today, the law of Smurfs is a law. What's the law of Smurfs? Don't know. But the deal is there's no one arbitrary body that decides all of that. It's the consensus of the scientific community. And oftentimes the fact that something is a law is uncovered because of its repeated assumption to be true without additional testing, without additional work on the theory. It's just presumed to be true, and so we find ourselves down the road with a consensus that it's a law. A bunch of words, a lot more words than are in the book, but hopefully that helps you understand the nuance between a hypothesis, a theory, and a law. All it is more and more testing, more and more apparent validity of its truthfulness, and a law's absolute truthfulness. Experimentation in the scientific method. There's a brief outline of this on page 36 with a basic sequence that we follow. First of all, I'm doing some kind of experiment. I've got to ask myself, what is the question I want to answer? What's the purpose for what I'm doing? And these 5 points are on page 36. What do I want to answer? What do I think will happen? This is the question I want to answer. I'm going to set up an experiment. This is what I think is going to happen. It's important for you to write down your hypothesis before you do the experiment. If you remember the first couple experiments I did here in class, kind of like I'll do it, you watch, and you practice writing down a few things. And I said, write down what you think is going to happen. A couple of those experiments, hopefully you sat there and go, duh, I know what's going to happen. It's so obvious. Well, you know what? You got to get in the habit of writing down what you think is going to happen before it happens. That way you can prove that your thinking was correct beforehand, not be like everybody else and go, oh yeah, I get that. Of course, I see that. It's easy. It's kind of like when I work a problem on the board up here, right? You don't have a clue how to do it, but once I do it, you go, oh, it's so obvious. Yeah, anybody can do that. But wait a minute. Just 2 minutes before, you had no clue how to do it. How come suddenly it's so obvious and clear? So if you ask yourself the question before you do the experiment, what do I think is going to happen based upon your hypothesis, right? This is what I'm thinking in mind. This is what is at play. This is what I think is going to happen. Boom, when you do the experiment, you go, oh, it worked. Some part of my thinking was right. Or you go, oh, it failed. What part of my thinking needs to change? Write it down in advance. And for some of you, I need to think, right? I need to think before I do it, as opposed to just do it and then make it up on the fly afterwards. So you're kind of testing your thinking when you do the experiment. You're going to test the hypothesis by actually doing an experiment. As simple as, I believe when I let go of this clicker, it's going to fall on the ground and break. It fell on the ground and broke. That's what I thought was going to happen. Okay. There's some truth behind my thinking because what I observed in my testing validated what I thought in advance. Now that doesn't think what my thinking was in advance is all correct. There's some element of it that's true. There's some element of it which is correct. So after I do the experiment, I'm going to go through and analyze it, my results. I'm going to look at my results and I'm going to say, hey, these results align with my thinking. These results, not so much. How can I test? How can I work to improve my understanding of the phenomenon that I'm watching? How can I come to understand it better? What should I do? And something very similar to analysis is the conclusion. Here's the two different parts of it. In the analysis, you look at the data to uncover. In the conclusion, you use words to describe what you determined in the analysis. They're close. If you read them real quickly, you're like, determine the results and plan future actions, describe the results and future actions. They sound like the same thing. No, not really. Here is discovery. Here is presentation. If I'm reading a report, like I'm reading a journal article, and I'm going through this journal article, and they do this experiment, and then after that they give a summary of what they did with all the data. And if you're a techno-geeky kind of person, you're in there reading all the numbers, and there was this percentage and this correlation, and the end number was this, and you're looking at all this stuff, and you're like loving the analysis, because as you're looking at the analysis, you can see where the conclusion is going to come from. But at the end of the analysis in the research journal, they're going to say, conclusions. Boom. Here's what we conclude. And as you read the conclusions, it's a nice, lots of words using prose to explain to you what they found. What they found was also what they showed you in data form just before that. But in the conclusion, you're going to put it in a language so that you can communicate it to people that don't know the field, but they're reading your work. So think of it this way. In the analysis portion, you're writing for if you're writing it, you're writing for other scientists. And if you're not writing it up in this way, like a journal article, you're just looking at the data yourself to pull out your conclusions. Then, once you've pulled out your conclusions, you need to write it in a format that anybody could read and understand, in words, not numbers, not percentages. Tell me what that means in prose, in real words. That's the conclusion. Okay? So they're similar, but your conclusion is a verbal presentation of what you uncovered mathematically in your analysis. Boom. We've completed Module 1. So, let's go ahead. We have 25 plus minutes. And if everybody's in agreement, see, here's me being slightly democratic. Is everybody in agreement? Just go ahead and let's push through some of the review questions that you've already turned in. And then go to the practice problems that you've already turned in. We'll just complete the day by going through those questions and talking about the answers. We'll pick up tomorrow at the end of whatever we get through today. We'll include the homework for tomorrow on tomorrow's discussion. After that, my plan is to answer your questions and to work as a class, maybe in teams or in pairs, on extra practice problems, and still have the exam on Friday, not pull it up on you. I'm really tempted to do it Thursday, but I'm going to leave it where it is and give you an extra day. If you're bored in here, you don't need to review. Pre-read Chapter 2 during class time, bell work, whatever, okay? Or exit work. Shall we? Okay. With no major protest, review question number 1. We'll just follow in the book, so we're on page 41. Review question number 1. Which of the following contains no matter? Yeah.
3 and 4.
Both 3 and 4. Right. Both 3 and 4 contain no matter. We've talked about this a couple different times. I've already referred to it today. But heat and light are energy, not matter. Now, we get into physics and quantum physics and everything like that. We can start talking about the theory of relativity and talking about transfer between matter and energy and speed of light and weird stuff like that, okay? For the scope of this course, and we'll often say that, for the scope of this course, heat and light, these energy forms, have no matter. Part of the reason why I look at that, to me they're not exactly the same, but they're similar in that light and heat, again, transference of energy, and in my mind, things like light waves, TV waves, radio waves, all these forms of energy are just different wavelengths or frequencies, whichever way you look at it, in the electromagnetic spectrum. In the book later on, when we get to that module, you'll see that the authors of this book don't differentiate between radio waves, TV waves, and light. They call them all light waves. At least that's the best I can recall. So that fine line of distinction isn't there. They're energy waves. They're part of the electromagnetic spectrum. So, too much information for Module 1. But anyway, these two, heat and light, do not contain matter. A baseball and a balloon full of air. This was the trick for day 1, right? Do fish know they're in water? Is there anything around you right now? No. Yes, there is. There's air around you. You have matter touching all parts of you right now. That's not part of you. Review question number 2. List the basic metric units for each one of these measurements. And again, I'm okay with, I'm not necessarily going to call on everybody, so I'm fine if you want to participate. I almost brought in the beach ball. I went over to Miss Bryan and borrowed her beach ball so we could pass the beach ball around, and like you could determine, you answer a question and have the next person answer the next question. Maybe we'll pass the globe around. How would that be? Or some other mechanism. Throw a marker? Well, see, if we throw a marker, we've all got to wear chemistry goggles. That's one of my rules in here, too. For some of you, it'll be improvement. But, huh? Don't assume I'm talking. Don't assume I'm looking at you or talking to you all the time, okay? It's okay. Okay? The basic, or the base metric units for length is what? Just go ahead. What is it, class? It's a meter, right? Abbreviated with a small m. Mass is in grams, abbreviated small g. Time. What is it in the English system? Oh, good. We've got it down. Even though you didn't answer, I know you know it now. I occasionally will abbreviate that with SEC. Technically, it's just S, but SEC, I will accept that as well. And also volume in liters, liters is the capital L, not the lowercase l. Just remember the abbreviation for liters is a capital L. The prefix milli, as in millipede. How many legs would a millipede have? But no, it's not exactly true because you would assume 1,000, but milli doesn't mean 1,000, does it? A milli is 1,000th, or abbreviated 0.001 in decimal form. So a milli is a thousandth. Centipedes and millipedes, I don't know how many legs they have exactly, but you know. Which do you think has more legs, a centipede or a millipede? A millipede would have more because it's got, the milli means, we think of it as 1,000 and a centa being 100. So millipede, centipede, ped meaning feet, right? You go to the podiatrist for your feet, so a millipede, so a centipede. So what's the prefix? Prefix means a milli is 1,000th, abbreviated 0.001. And that's what we need to remember when we do our conversion factors. Milliliter is 0.001 liter. Replace the prefix with its decimal form. Okay. All conversion factors, when in the form of a fraction, must equal 1. Okay. Some of you got into the derived units thing. Must equal the numerator units divided by the denominator units. And remember, the concept of a conversion factor is that it's something divided by something of equal value. And something divided by something of equal value is equal to 1. That's why we can say we're not getting more or less, we're converting it into some other language. We're changing the way we're describing it. We will change the number, and we will change the units, but we won't change the value when we convert it. Okay? So, when in the form of a fraction, conceptually, conversion factors are always equal to 1. Anybody have a question on that? Because I know there was some struggling with that on the homework. Conversion factors are equivalent to or equal to 1. Granted, 1 liter divided by if we have 1,000 liters divided by 1 kiloliter, it looks like 1,000, right? But its value is, since they're equal, it's equivalent to being 1, something divided by itself. Which has more liquid? Just for a moment, just so everybody can remember. A glass holding 0.05 kiloliters or a glass holding 12,000 milliliters. In your mind, convert them to liters. How many liters are in 0.05 kiloliters? How many liters is 0.05 kiloliters? How will I convert kiloliters to liters? Oh, you're killing me here. Oh. Okay. So if I know that a kiloliter is 1,000 liters, I can take the decimal place and move it 3 places to the right and call it liters, right? 0.05 kiloliters, 1, 2, 3 is 50 liters. Because if I multiply that by conversion factor of 1,000 liters over 1 kiloliter, I'm multiplying it by 1,000 to convert it into liters. I can take the kilo and eliminate that by moving the decimal place 3 to the right. 3 to the right would be 50 liters. So a glass holding 50 liters, or let's convert 12,000 milliliters into liters. I would go ahead and move the decimal place which direction now? Go ahead. 3 to the left. Here. So which has more? 50 liters or 12 liters? Yeah, 50 liters is more fluid than 12 liters. Now on paper, if you didn't see that, you had to work it out. Hopefully you had 0.05 kiloliters times 1,000 liters per 1 kiloliter, and you would have done the math and had 50 liters. And then below that, 12,000 milliliters times 1 milliliter over 1/1000th of a liter, and that would give you 12 liters. And you say, which is more, 50 liters or 12 liters? 50 liters is more. And we need the book for this one, number 6. How long is the bar in the picture below? Take a look at that if you're on page 41. How long is that purple bar? What did you put? 265? Any other answers? How precise can you read it given the markings on the instrument? It's to the 10th, so we could read it to 2.6. If it was 2.7, but we're saying it's somewhere between 2.6 and 2.7. If you had 3.6 or 3.7, you forgot that you're starting at the 1 and not the 0. Okay? So if you wrote 3.65, which is 2.65 is the answer. If you wrote 3.65, it's because you forgot to take off the 1, because you're starting at 1 and not at the 0. The most common error, forgetting to take off that 1. Second, you could read it to 2.6, you could read it to 2.7, but since you can read it to 2.6 or 2.7, you are required to take it to one more decimal place than you can read directly. So it could be 2.6, but it's more than 2.6. It could be 2.7, but it's shorter than 2.7. So you have to estimate where it is between the two. And so that 5 in the hundredths place is your estimate. 2.6 and a little bit more, which is about halfway, make it 2.65. Right. Number 7, a known mass of 50 grams. Again, these are the same questions, just kind of simplified a little bit. A known mass of 50 grams. Student 1 takes that mass and determines that it's 49.8123 grams. Student 2 says it's 50.1 grams. The questions are, which student is more precise? Go ahead. Student 1 is more precise. Somebody else, how do I know? Why is student 1 more precise? Ma'am?
Because he didn't round it up, he took it all the way.
Right. We're going to assume that he didn't make it up, right? So actually read the instrument to be 49.812 and then estimated 3/10 of the way to the next marking and gave us an answer of 49.8123 grams. Student 1 is precise to the, not the tenths, hundredths, thousandths, is precise to the 10,000ths place. Student 2, however, is precise to the 10th place. The assumption there is that their instrument could only read to the 1's place, and they had to estimate to the 10th place. The assumption for student number 1 is that their instrument could read to the 1,000th place, and they estimated to the 10,000th place. Which one of those students had a more expensive piece of equipment? The first one, because you're going to pay for the precision. It's harder to make it than the ballpark even grams, or get something that can go down to the hundredths of a gram. This is going to cost you more because it takes more engineering, it takes more precision in the creation of the tool to read that level of precision. Okay, so student 1 was more precise. Now, which student was more accurate? Ma'am? Student 2 was more accurate. And how do we determine accuracy? How close to being correct. We were told that it was a 50-gram mass. Somebody said, this is 50 grams. Okay. Then the person that's the most accurate is the person who's closest to getting 50 grams. Student 1, 49.8123 grams, that student is off by 0.1877, right? Student 2 is off by 0.1. You could look at student 1 and say, they're off by more than 0.1. Student 2 is only off by 0.1. So even though they have a less precise instrument, their answer that they put down is closer to being the true answer, so they are more accurate. Any questions? And please, before I move on, if there are questions on that, go ahead and speak up. Conceptual problems, speak up. But the precision is going to be reflected by the digits that you can measure on the instrument. It's going to be reflected by how far or what position the last digit is in. And accuracy is going to be how close to being correct. This is kind of like the archer who has the really bad bow but still gets a bullseye. And this is like the student who has a really incredible bow, but their process is off. And so they're not shooting as well, even though they've got better gear. That's the analogy. So great gear doesn't guarantee a bullseye. So the accuracy is normally based on the operator, precision based upon the instrument. Number 8, I just referred to this. What's a sig fig? A sig fig is a measured digit that comes from a measuring instrument. And I qualify that by plus 1 digit, plus the one you estimate, because your estimation is based upon what you read from the instrument as well. So once we know the significant figures for a measurement, we can use it. We've talked about how to use it in math, how to determine how many there are, and all that kind of stuff. But where does it come from? Just like in the last example, it came from the precision of the instrument. So we read the numbers from that instrument, and we can be as our precision is limited by the precision of the instrument. And everything that we can read with appropriate precision is significant. Number 9, how many sig figs are in each of these numbers? Now we get to the fun stuff, right? This is the stuff where we're like, oh, okay, I got this thing in my mind, and I go through the different steps. And there's 4 different steps to determining if a figure is significant or not. And so I can boom, 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 hit all of those and come up with a single answer. So for the number 120,350, how many significant figures are there? Get a number in your mind. I'm just going to reveal it in a minute. Ready? 3, 2, 1, boom, 5. Anybody disagree with that? Okay. The non-zeros are significant. So the 1, 2, 3, and 5 are significant. The 0 between the significance is significant. So the 0 between the 2 and the 3 is significant. There are no leading zeros and now trailing zeros right of the decimal place. Are there any? None. No. So there are only 5 significant. Some people thought 6. Sorry. Trailing zeros have to be to the right of the decimal. There is no decimal. There's an implied decimal, but there is no decimal. 10.020. Number of sig figs is, boom, 5. Okay. Question? No? Excitement? Okay, good. So the 1 and the 2 are non-zeros. They're significant. There are no leading zeros. The 2 zeros on either side of the decimal place are intermediary zeros between significant figures. And the 0 on the right is a trailing 0 right of the decimal point. It is significant. So there are 5. Number 3. 0.000000012. There are 2 significant figures. Okay? Leading zeros are not significant. Non-zero digits are significant, so the 1 and the 2 are significant. Trailing zeros, there are none. Trailing zeros right at the decimal place, there are none. And there are no intermediary zeros. So this number has 2 significant figures. And the last one. Scientific notation should be really simple, right? Because in sci-fi notation, scientific notation, every digit that's presented is significant. That's the definition for scientific notation. You record every significant digit. So how many digits are there? There are 3 digits, right? This number here before the times 10 to whatever power, that's telling you every significant digit in the number. There are 3 significant digits in 7.20 times 10 to the second. Why? Because there are 3 digits in that number before the times 10 to the power. If we work the other way, we would have to represent it as 7.20. 7.2 is not enough. That would only be 2 sig figs. It's got to be 7.20. Because somewhere we've said that there are 3 significant figures in this measure. True or false? It says in here that the student measures these 2 things, adds them together, and gets that number. Is this student correct? Is this a true answer or a false answer? 251 grams. That 50.3 grams and 200.24 grams is equal to 251 grams. That's wrong. Because when you look at it, the actual math is that 50.3 plus 200.24 is 250.54 grams. Forgot the G, sorry. The 250.54 Smurfs. No, 250.54 grams. But what is my rule about addition and subtraction? Go ahead. The precision of your answer has to go to the same precision as the least precise of the measures that make it up. So in both of these measures, the 50.3 goes to the tenths place, the 200.24 goes to the hundredths place. The least precise is the tenths place. So when I do the math, I look to the tenth place, look to the right of it to find out if I should round up or not. In this case, I don't, because the hundredths place is a 4, and so I leave it as 250.5 grams. Now, did the student get 250.5, maybe 250.54? Probably, and decided, you know what, I'm still in elementary school. I'm going to round it up to the nearest number. No. Now you've created error. 250.54, likewise, introduces error. The answer is 250.5 because of the precision of the least precise measure.